Welcome everyone to today's presentation, System Safety, a practical application of safety methods and principles. Throughout this session, we'll explore effective safety methods and their practical applications to manage risks and protect lives. Let's dive in. A hazard matrix is a powerful tool used in safety and risk management to evaluate and prioritize risks systematically. By combining the likelihood or probability of a hazard occurring with the severity of its potential outcomes, the matrix provides a clear, visual way to assess overall risk and determine appropriate mitigation measures. Let's break it down into its key components. The probability scale measures how likely it is for a specific hazard to occur. This is often divided into levels such as frequent. The event is expected to happen regularly or repeatedly under normal operations. Probable. The event might happen occasionally over time. Remote. The event could happen, but not frequently. Extremely remote. The event is unlikely but still possible. Extremely improbable. The event is so unlikely that it is almost inconceivable. The scale helps quantify the likelihood of a hazard, providing the first axis of the matrix. The severity scale assesses the impact of the hazard, should it occur. This is typically categorized into levels such as catastrophic, results in multiple fatalities, total system loss, or severe environmental damage. Hazardous. The hazard leads to serious injury, incapacity, major system damage, and outcomes that may overwhelm safety systems but fall short of catastrophic impact. Major. Causes significant injury, system damage, or operational delays. Minor. Leads to minor injuries, system degradation, or manageable disruptions. Minimal. Results in negligible harm or inconvenience. This scale forms the second axis of the matrix, reflecting the consequences of the hazard. The composite of probability and severity components combine in an intersection of the severity column and probability row to a resultant risk score of high, medium, or low safety risk. To better understand the relationship between causes, hazards, probability, severity, and mitigation controls, let's examine an example involving loss of situational awareness leading to a fall hazard. This table structure breaks down the analysis into key components, guiding us through the hazard assessment and control process. Incorporating this analysis into a table structure helps visualize risk reduction. For example, the initial risk without controls is high risk with probability frequent, and severity, catastrophic. Assessing the residual risk with application of rule-based controls as mitigation remains high risk with probability of probable, less likely than frequent, and severity component of catastrophic. By addressing both likelihood and severity, the controls ensure that the risk is managed comprehensively. It is worth noting that the use of simple rule-based mitigations, in this case, a rule to remain 10 feet from the roof edge, is considered a weak mitigation and does not provide a robust control to reduce the probability or likelihood of the hazard. A reduction in terms of orders of magnitude in likelihood, from frequent to probable, is generous credit given to the effectiveness of the mitigation, but illustrates the application in the hazard analysis table. The root cause in this case is a loss of situational awareness. This might occur due to worker distraction, fatigue, multitasking, misleading signage, or being in an unfamiliar or poorly designed workspace. For instance, a worker might step too close to an unprotected edge while focused on another task. Situational awareness is neither the hazard nor a mitigation that can be applied to directly affect either the probability or severity of the hazard. Rather, it is insufficient situational awareness that is a causal condition for exposure of the hazard. This misconception has frequently resulted in confusion regarding the application of mitigations involving situational awareness. Not all safety measures are equally effective. Some solutions eliminate hazards altogether, while others rely on human actions, making them less reliable. Let's break down the hierarchy of safety mitigations, from the most effective to the least, so we can focus on what truly keeps people safe. The most effective safety approach is designing hazards out of the system. Safety by design. Redundancy. Backup systems ensure functionality even if one part fails. For example, dual hydraulic controls in aircraft allow control of an aircraft even if a pump fails or hydraulic lines rupture. Fail-safe. A fail-safe design ensures that if a failure occurs, the system defaults to a safe state. For example, train brakes activating when electrical power is lost. Fail operational. Fail operational means that the system continues working despite failures as is implemented in triple redundant flight control computers. Design-based mitigations work because they require no human intervention. They simply prevent failures or minimize their impact. Safety devices. Next in the lineup is safety devices. When hazards can't be eliminated by design, safety devices step in. If a failure happens, the system should catch and correct it. Interlocks, for example, prevent unsafe actions such as a machine that won't start if the safety guard is open. Reversionary modes, or switching to backup operations, can help in case of failure. Usually with degraded functionality, and automatic cutoffs will stop a process when danger is detected, like circuit breakers prevent electrical fires. Safety devices work because they can react faster than people and reduce the need for manual intervention. Warnings and cautions. Then come warning and caution systems, which are helpful but not always enough. Alerts only work if people notice and respond to them, and if false alerts are rare enough that they are not disregarded and become ineffective. Alarms and alerts indicate dangerous conditions like smoke alarms, and check engine lights notify users of a potential issue before failure. Proximity sensors can warn of obstacles but won't stop collisions. Warnings are less effective because they require human response, and people can miss or ignore them, especially under stress. Procedures and training. With mitigations that require interaction, procedures and training are necessary but are human-dependent. People make mistakes, even with training. When hazards can't be eliminated or automated, we rely on standard operating procedures or guidelines to follow for safe operation. For example, crew resource management improves teamwork and decision-making, and emergency protocols help with steps to handle system failures safely. But people forget training, make errors, or skip procedures under pressure, making training necessary but not fully reliable. Rules and policies. Finally, last and least, we have rules and policies. The go-to catch-all. Policies are only effective if people follow them 100% of the time, but people tend to ignore or forget them. Compliance relies on individuals making the right choice every time, and they do nothing to physically prevent hazards. A rule to remain 10 feet from the edge of the roof doesn't stop someone from choosing not to in order to cut corners, or simply becomes disoriented focusing on other tasks and loses track of where the edge actually is. In summary, safety by design is the strongest mitigation, followed by safety devices in the event of critical system failures, followed by warning devices with protocols and training. Then the least effective are rules and policies, which are often favored because they are fast and cheap, but in practice, effectively provide little safety mitigation. Let's delve deeper into the hazard of a fall from height and examine its worst credible outcome. In the context of safety analysis, the worst credible outcome for a fall from a building is an individual impacting the ground, resulting in fatal injuries. This scenario underscores the critical severity of such an event, categorized as catastrophic in hazard assessment. A fall from height represents one of the most severe hazards in occupational safety. Studies such as Lapistole et al. Research on vertical falls show a 100% fatality rate for falls from 8 stories, 90, 100 feet or higher. Given the catastrophic nature of the outcome, the only acceptable likelihood for such an event occurring is extremely improbable, a level of probability so low that the risk is effectively mitigated. Achieving this level of safety requires the implementation of robust, multi-layered mitigating controls. To understand safety controls, we'll use a metaphor: moats, ropes, nets, and fences. These represent different methods of managing risks by addressing severity and likelihood. Each approach serves a unique purpose in mitigating the impact of the hazard. Let's delve deeper into the role of environmental or system state controls, symbolized here as the moat. In the context of hazard analysis, these controls address the conditions or environments that influence the occurrence or impact of a hazard. For instance, consider how a moat around a castle doesn't stop attackers, but changes the environmental conditions, making an assault more difficult and less likely to succeed. In safety terms, this means modifying the system's operating environment to reduce risk severity if the hazard occurs. When we analyze hazards within a safety matrix, this environmental control affects the severity column. It reduces the consequences of an event by altering conditions to lessen the impact. For example, in the case of falls, a moat-like control could be soft landing surfaces or energy-absorbing materials. These won't prevent the fall, but reduce injuries, shifting the risk from catastrophic to, say, major or minor. In the safety matrix, using a moat-style control might lower the overall safety risk by reducing the severity score. For example, shifting a risk from high to medium or even low, depending on its application and effectiveness. While moats don't change the likelihood of a hazard occurring, their ability to influence severity makes them an important component in comprehensive safety planning. However, there are limits. At certain heights or conditions, such controls may no longer be effective. For example, past a critical height, even the softest surface may not mitigate injury severity. This limitation must be identified and documented during hazard analysis to ensure realistic risk assessments. Now let's explore nets, which represent a mitigation control that works after a hazard has occurred. Nets function as a safety mechanism designed to catch or contain the hazard's outcome, reducing its severity. Unlike a moat, which modifies the environment, nets directly interact with the hazard's effects. In hazard analysis, nets are particularly effective at mitigating severity within a safety matrix. For instance, in the context of fall hazards, a net doesn't prevent the fall, but minimizes the injury sustained by stopping the descent before it reaches critical severity. If properly placed and maintained, a net can move a risk from catastrophic to major or even minor severity. However, like the moat, nets have limitations. They do not prevent the hazard itself. The fall still happens. Additionally, their effectiveness is bounded by placement, strength, and the specific conditions under which they are used. This emphasizes the importance of integrating nets with preventive controls to comprehensively manage safety risks. Next, let's discuss ropes, symbolized here by safety harnesses and restraints. These controls serve to arrest a fall mid-event, reducing the severity of the outcome. Unlike nets, which passively catch the fall, safety harnesses actively restrain or stop the individual during the fall process, preventing catastrophic consequences. In hazard analysis, safety harnesses are categorized as active mitigation controls. They address the hazard after initiation, reducing the severity of the incident and sometimes indirectly lowering its likelihood by deterring unsafe practices. For example, workers are more mindful when wearing a harness. Let's examine how harnesses function within a safety framework. Safety harnesses stop a fall in progress by absorbing and distributing the fall forces through the system. This reduces the impact on the individual, preventing catastrophic injury or death. In the safety matrix, this directly lowers the severity rating by mitigating the hazard's worst credible outcome. Unlike nets or moats, harnesses are worn by the individual, providing a mobile safety solution. They require proper fitting, connection to an anchor point, and awareness of usage conditions. This mobility can reduce secondary risks, such as entanglement, but also introduces new considerations for hazard analysis, such as incorrect usage or improper anchoring. While harnesses reduce severity, they rely on correct usage to function effectively. For example, improper anchoring can fail to arrest a fall, rendering the control ineffective. These residual risks must be identified and mitigated with training, supervision, and routine inspections. Let's discuss fences, which represent a proactive mitigation control in safety design. Unlike other controls that reduce severity after a hazard occurs, fences aim to prevent the hazard altogether. In hazard analysis, fences are classified as preventative measures because they directly reduce the likelihood of an event occurring. Let me say that another way, the fence does not reduce the severity of the hazard. A fall from the height would still be catastrophic, but the fence reduces the likelihood of falling in the first place. Fences physically block access to hazardous areas, creating a clear boundary that prevents exposure to the hazard. For example, a fence around a rooftop prevents individuals from reaching the edge, eliminating the risk of falls from height. This reduction in access is reflected in the safety matrix as a decrease in likelihood. By clearly marking hazardous zones, fences influence human behavior, discouraging unsafe actions. Combined with signage or alarms, fences create an additional psychological deterrent to crossing into danger zones. Fences also operate without requiring human action or intervention. This makes them reliable and consistent controls, as they are not dependent on proper usage or human compliance, like harnesses or nets. Fences only prevent hazards within their design scope. For example, a fence may block access to one area, but could be ineffective if individuals climb over or bypass it. Hazard analysis must account for these potential bypass scenarios and ensure complementary controls, such as surveillance or alarms, are in place to address these risks. To conclude, here are some pro tips for effective safety management. Clearly define the system and its hazards. Focus on the hazard, not its causes or effects. Use data, not anecdotes, to evaluate risks rationally. Validate mitigation controls, ensure they truly perform as intended. An increasingly effective way to enhance safety and eliminate fall hazards is by designing systems or processes that remove the need for humans to physically occupy elevated spaces. By leveraging alternative approaches to perform functions traditionally carried out by individuals, organizations can reduce or eliminate the risks associated with working at height. Removing personnel from elevated spaces aligns with the hierarchy of controls, where hazard elimination is the most effective strategy. If there is no human presence in a high-risk area, the likelihood of a fall becomes zero, and the need for fall arrest or mitigation controls diminishes. Thank you all for your time and attention today. I hope this has provided valuable insights into the principles and practical applications of system safety. By understanding and implementing effective safety controls, we can not only protect lives, but also foster a culture of proactive risk management. Let me leave you with a quick safety anecdote to emphasize the importance of vigilance. A worker in a manufacturing plant was tasked with inspecting elevated machinery every shift. For years, they faithfully wore their harness, but thought the safety net below was redundant. One day, while performing their routine inspection, a misplaced tool caused them to lose their footing. The harness snapped into action, but the worker panicked, trying to regain footing and inadvertently released the latch. It was the safety net that ultimately saved their life. The lesson here is clear. Safety controls work best when layered and designed with human factors in mind. Even when everything seems under control, the unexpected can happen. It's our responsibility to ensure every layer of protection is in place, validated, and respected. Thank you again for your engagement. Let's continue to prioritize safety in everything we do. Stay safe and take care.